23.4, which we started discussing in the previous class but haven't finished, right? So let me quickly remind you this situation. We have 2-point charges, Q1 and Q2, negative, positive. Of course, they create their own electric fields. Right? As a result, the whole space will be filled with the electric field, okay, net electric field, which is basically superposition of two fields. And in this case, the problem asked about finding electric field at this particular point, which is 5 centimeters away from this charge Q2. The distance between these two charges is 10 centimeters. So immediately we introduce coordinate system because we have to deal with vectors. Whenever you work with vectors, you must introduce coordinate system. Right? Okay, so we introduce coordinate system, and the most convenient origin is at the point in question. Okay, so then in order to have a complete picture in front of us, so we drew all vectors. So first, electric field created by this charge, and then E1 electric field created by that charge, right? And then E, that's what we need to find. It's a net vector, net electric field. All right, and then we discuss strategy. Strategy is exactly the same like in the problem in the first class, where we wanted to find the net electric force acting on the charge. So pretty much, what's the difference between this problem and that problem? In that problem, at this point, we had some charge, and we wanted to find the net electric force acting on that charge. Now we don't have the charge. So now we have just empty spot, right? And we want to find the electric field. But from the mathematical point of view, these two problems are almost identical. Mathematics doesn't care about the nature of the vectors, right? It doesn't care if it's a electric field vector or electric force vector. It just knows, okay, it is a vector, and I will treat it as a vector. That's it. That's what mathematics needs to know. So from the mathematical point of view, problems are almost strategically the same. So we're going to apply the same idea. So first we can find the magnitude of this force, field, magnitude of this electric field, then components, then magnitude of this field, and components, like we did in the first lecture. And then once you have two vectors presented in the component form, it's a piece of cake to find the net, in this case, electric field vector, right? So let's do it. And of course, we need to use the formula which we derived in the previous class, which give us a magnitude of the electric field created by a point charge. And since we have point charges, we can apply it safely. All right. Okay, so I will put a small bullet. You know what? I'll move this charge Q1 closer to get more space. So first bullet, I will deal with with electric field E2. So first magnitude, and this time I will move a little bit faster. So it will be K, okay, I will use the absolute values everywhere. Because again, this is the formula for the magnitude of the electric field strength. And R2 squared. What is R2? It's at this distance, which is B, right? So I will just open my explanation box and show that R2 equals B. And of course, don't forget to convert to meters. Meters must be used, right? Okay, this time, of course, I'm not going to plug numbers. You can easily do it by yourself. You know what? Let me remind. So it will be 5 times 10 to the power of minus 2 meters to be safe. Right. Okay, so if you calculate it, and again, nanocoulombs, okay, this nanocoulombs, 3 nanocoulombs, nano 10 to the power of negative 9, don't forget. The answer will be 1080. 10,800 units. You remember, there's no special unit for the electric field. You remember we discussed that discrimination situation. So whatever you see in the definition of the electric field, force divided by charge, so newtons divided by coulomb. Newtons divided by coulombs. So, And so now we need to write components. And of course, in this case, it's simple because we see that electric field is along x-axis. You know what? I want to save space, and maybe I can squeeze over here. Okay, I will write it here. So E2x will be 1080. I mean 10,800, and E2 sub y equals to 0. Right? So again, let me frame it with green. It's not the final result, but we will need it at some point soon. Okay, now let's do the same with E1, first magnitude. E1 equals k absolute value of Q1 divided by R1 squared. R1, it's this distance, right, from this negative charge to the point in question. So this is R1, right? So of course we need to apply some efforts in order to find it. But of course it's a piece of cake. We know this, and this is the right triangle. So Pythagorean Theorem, right? Who doesn't know that? So R1 squared equals a squared plus b squared. Right. Okay, let me write. It will be 125, right? R1 squared equals, so square of this will be 100 plus 25, 125 meters to the power of 2. Okay, let me close my explanation box. No. What is wrong? Just now, immediately I noticed. I have to be careful. No. This is not meters. This is centimeters, right? But of course, you need to convert to centimeters. I mean, to meters, sorry. Yeah. Okay. So basically, it will be times 10 to the power of negative 4 to convert to meters squared. And so if you calculate it all, you will end up with, where are my notes? 4,267. Okay, I use Mosig fix 0.2 newtons per coulombs. Okay, now components. In order to find components, we need to introduce one of the angles. Either this or that, they're equally good. I cannot say anything against any of these angles. In my notes, I used this angle. I decided to use this angle theta. Okay, so we need to find it. And again, from the right triangle, I will use again tangent. Right, you remember tangent of an angle, it's a ratio of opposite side versus adjacent side in the right triangle. So in this case, it will be A over B. This is opposite, that is adjacent. Right, so let me write that down. Tangent of theta equals to A over B. And of course, numbers are given. It will be tangent of arctangent of 2 because A 10, B 5, so ratio is 2. And you will get theta. Where is it? Where is my theta? Okay, 63.43. Again, I use Mosig fix because this is not the final result. Keep slightly Mosig fix. And then round it off only at the very end. Okay, components. Now, once we know that angle, so we can find E1x. So effectively, it's this component. Okay, which color should I use? Okay, blue. So it's that component, right? And from first class discussion of the first class, I'm sure that now you know which sign should go over here in front of the expression which I'm ready to write. Right. it must be negative, because that component, you see, x component, points in the negative x direction, because we don't use conventional angle, we use a convenient angle, right, in order to find components. So we have to take care of pluses and minuses manually, right? So there must be minus, right? So minus, and we need to find x component which is adjacent to the angle, right? So we have to use cosine function. Opposite side, if you want to find opposite side, then of course you need to use sine function. In this case, adjacent side, you need to use cosine function. So it will be E1 times cosine of angle. Okay, E1 is given, is found, theta is found. So you can again multiply them up, and you will get minus 1908, okay, 68. And again, just newtons per coulombs. For now, newtons per coulombs. In a few classes, we can also write that as volts per meter, but we haven't introduced volts yet. Okay, so now let's do the same to find y component. And y component, it will be this straight down component, right? Negative again. So again, we use convenient angle, not conventional, so we have to put minus manually. So it will be E1 times, and so this side, which is also over here, right? So it's opposite to the chosen angle. Opposite side, sine function, sine theta, and number will be 3816 negative. And what's after decimal point? 5.3 newtons per coulomb. Okay, so this is our these are our components of the second vector. So here first vector, second vector. So now in order to find net vector, we can just need to add them up, add corresponding components up. So first I will write in the vector form, E1 plus E2. And now components. So E sub x will be E1x plus E2x, right? Okay, E2x, E1x, so of course you have to subtract them, because this is negative, that is positive. Again, I'm not going to write numbers. The answer will be 8,891.32 newtons per coulomb. Again, I still keep more sig fixed, because at the end we will have to find magnitude of this vector and direction. That's the final result in this question, in this problem. And the y component will be E1y plus E2y. And in this case, it's simple, because this is 0. So it will be just that minus 3,816. Right. Okay, pretty much at this point, yeah, once you know components of a vector, you know everything about that vector. But the problem wants to get the strength of this net electric field and then direction. And again, I want to remind you what we found. We found what are these EX. It's this picture becomes too complicated, right? So this is EX, right? And this will be E sub y. These are components of this electric field vector. So in order to find magnitude of this electric field, so we need to use just Pythagorean theorem. EX squared plus EY squared. You see, very similar to the problem in the first class. So E, you see, there is no vector on top. It means it's a magnitude of the net vector, net electric field vector. So square root of EX squared plus E sub y squared. And again, numbers are here, so you can calculate. I will just write down the answer. It will be 9,000 675, okay, 0.8 newtons per coulomb. Again, so how many sig figs? Just read mastering physics statement of the problem properly. Right. So here I use 5 sig figs. Okay, so that's the magnitude. Now direction. In order to find the direction, we need to introduce another angle, usually relative to the x-axis. So let's introduce this angle phi. Right. And again, like in that problem from the first class, tangent of phi, it will be opposite side, which is a y component of this electric field, versus adjacent side, which is x component. Right. And again, I'm going to use just the absolute value of the components because, yeah, we're just working with this triangle, right? All right, so tangent phi equals to absolute value of E sub y, right? Yeah, opposite E sub y, adjacent E sub x. Can you still see it? Yeah. Okay. So from here, of course, you can take arctangent, and you will end up with angle 23.23. Okay, you can round it off to 2 sig figs. 23 depends how many sig figs problem wants to see. Okay, so again, the goal is to play a little bit with electric field, because I remember once, usually, not usually, at some point for several years, I gave a similar problem about finding the net electric field on the final exam, right? And students were quite happy about that and successful. But once I decided, okay, so what's the difference between electric field, electric vector? And I gave a problem like this, similar to this, to find the electric field, and students started panicking. Where's the the third charge? What can we do? What should we do, right? So it was, I was quite surprised that there was still not a clear understanding the difference between electric force and electric field. Okay, most likely you are quite comfortable now with the problems like this, right? And now let me, if you have questions, of course, ask. Then a couple of conceptual questions, and then I will switch to the presentation. So conceptual question, I don't remember where I got it. So no name, I mean no number. So I will just put new bullet and just write CQ, conceptual question. So what if we have this situation? Let's assume that we have electric field given by these electric field lines. Okay, so E. Okay, I tried, but not very successful. They're not very straight. And at least my intention was to have exactly the same density of lines. It means what? What's the name of this field? It's a uniform electric field, right? Uniform electric field. So that's what we have. Then, what if we take an electron and accelerate it, I don't know, with an accelerator, and shoot it into this electric field? So let's say this is electron. And I give you a few trajectories, right? So first trajectory, which color should I use? Okay, let me use black, right? So first trajectory, this way, then this trajectory possible, this trajectory possible, and you know what, let me add additional electric field line over here, right? And the last option, what if it moves this way? So 4 trajectories, let me label it like, I don't know, A, B, C, and D. Which trajectory, along which trajectory this electron is going to fly? It's almost like a multiple choice question, right? But just think for yourself. Which trajectory would you pick? Okay, I hope that you can justify. And then I will discuss it, and then I will bug you with some additional questions. Which trajectory electron is going to follow? A, B, C, or D? Okay, assume that there is no gravity. And you remember gravitational force is reasonably weak, so we can reasonably neglect it. Okay, so if there is no gravitational force, then of course there is only one force acting on this electron, electric force, right? Because electrically charged object, of course, is going to interact with the electric field. Right. And so as a result, we need to just know the direction of the electric force acting on this electron. And then, yeah, we can make a decision which trajectory is possible out of these four trajectories, right? So in the previous class, we wrote down one of the fundamental formulas in physics, right? Expression for the electric force. And it's this, right? So F equals to Q times E, right? One of the fundamental formulas in physics. So now we just need to apply it in our case. Look, we're dealing with an electron, which is a negatively charged particle. So effectively, we can write this formula, rewrite this way. F equals, let me show explicitly that that fact that the charge is negative. I can write it like this, right? Minus absolute value of the charge times E. Just to show that there is a minus in front. As a result, direction of electric field and direction of the force, electric force, are opposite. In our case, electric field is up. So it means that electric force acting on this charge is going to be down, right? So as a result, electric force is down. I preserved red color for the electric force as a major player in this game. So electric force will be down, and as a result, of course, the only trajectory which is possible, of course, trajectory D. And actually, it will be a parabola because it has a non-zero initial velocity. Okay, let me show that velocity is information about the velocity. So it flies with velocity v naught. Enters this field with velocity v naught. So D is the only possible trajectory in this situation, right? Okay, now let's play this. Imagine that you are an experimentalist, right? And this is your experimental setup, which is basically consists of, here you have an accelerator which can accelerate, let's assume, any particles. Then you have a freedom. It's your experimental setup. You can do anything you want, right? Then you can play with the electric field. You can change it, you can change direction, you can do anything you want. And let's say you can change also a particle. It's your setup, right? You can do anything you want. Let's assume that you have all the necessary equipment, right? So what would you change in order to get in the system? In order to get, for example, trajectory B, which changes. Which changes can lead to trajectory B? There are a couple of options, at least I see. Maybe you can see something else. Look, first, you can change, for example, if you want to keep electron in your system, right? You can flip direction of the electric field. You flip direction of the electric field, then of course electric force will be up, and of course your electron will follow trajectory B. What else can be done? For example, you can change your particle. Let's say you accelerate not an electron, but a proton. If you use a proton, then this orientation of the electric field, with this electric field, it will fly this way, because now you don't have that minus. With the proton, charge is positive, so direction of electric field and direction of the force are the same. So in that case, electric force will be up, and your proton will fly along trajectory B, right? Then, what can be done to get C? In this case, you can change, for example, you can use a neutron instead of electron or proton, right? If you use a neutron, which is electrically neutral, of course, a neutron is going to fly through the electric field without experiencing any electric force. It just doesn't care about the presence of the electric field because it doesn't have charge. So neutron, of course, will follow C trajectory. Or if you still want to have an electron, you can just turn off electric field, right? And of course, in that case, yeah, electron will fly straight without experiencing any force, right? Then, okay, now the last one, usually the trickiest one for students, right? Except I think once in one of the semesters, students immediately nailed the question, and I was really disappointed, right? Like bugging students, right? So how can we get trajectory A? What can be changed in order to get trajectory A? What can be changed? To get trajectory A, for example, let's say, okay, we want to keep electric field. Let's say we keep electric field in this this way. Then we have to make two changes. First of all, electron must be replaced with proton, right? And then what else must be added? We need to turn off your accelerator so that initial velocity would be 0. If initial velocity is 0, and here is a proton, of course it will just start accelerating and start moving that way because its initial velocity is 0, right? Or if you want to keep an electron, not a proton, if you want to keep an electron, then of course you will have to flip electric field and again turn off your accelerator so that the electron has a 0 initial velocity. Again, in that case, electron will start accelerating straight up under the influence of the electric force. Right. Okay, it's much fun to discuss this problem during the normal classes, normal semesters, right? When you can ask students one by one what do they think. Okay, so again, the goal of this question is to emphasize on the fact that charges can be positive and negative. Be careful about the direction of the electric force. Right. Okay, the next one is even simpler, but why mention? Why not? Let's mention it. So let's imagine that we have this electric field. Okay, guys, if something not clear, if you need any clarifications, right, speak up. So let's say we have this electric field lines. I should have asked that. Why not? Let's say these, and these. So these are electric field lines. You remember the lines which we decided to use to visualize electric field. Very useful, right? Very useful idea. So the question is, for example, let's say we have these 4 points, or 3 points. One, let's say point 1, let's say over here, point 2 and point 3. And the question is, okay, we're supposed to draw electric field vectors. These are electric field lines. Auxiliary, useful idea, but now I want to actually draw electric field vectors at this point, and that point. Again, electric field, again, it has what? Strength and direction. So we have to pretty much, the question is about that. So the students can draw the correct direction, approximately correct direction, and correct strength. If at some point electric field is stronger, then of course vector must be longer. If at another point electric field is weaker, of course the vector must be shorter, right? Okay, in this case, we need to remember stuff which we discussed in the previous lecture. So first of all, electric field is tangent to electric field lines all the time. Although whenever I give a question like this in a quiz, when we had normal classes, sometimes students drew electric vectors perpendicular to the electric field line, some other strange directions. So electric field must be tangent. So over here, tangent, over there, tangent. Okay, let me first draw it like this, right? Over here also will be tangent, over there also tangent. But I stopped drawing because now I have to be careful about the strengths of the electric field. You remember where is the information about the strength? In the density of lines. Here, density of electric field lines is larger, so electric field is stronger. So over here, I have to draw the longest vector. Of course, tangent. So let's say it's a E sub 3. Then here, density of lines is smallest. So my electric field vector will be again tangent, but the shortest. And at point 2, it's something in between, in the middle, right? Again, it will be tangent, but now it will be slightly longer than E1, but shorter than E3. So it will be E2 vector, right? Okay, it's very simple, basic, but this must be very, very clear in your heads, right? And you must be aware of all these simple things. But again, quite often during the normal classes, I give reasonably simple quizzes, and still lots of students draw some wrong directions. Okay, so pretty much that's what I was planning to discuss after previous lecture. And now let's switch back to the presentation and continue our discussions. Okay, I don't need this anymore. Okay, so what's the idea of today's class? So in the previous class, we learned how to find electric field created by point charge, okay, a point charge, right? Or if you have several point charges, right? Let's say if you have 2, 3 or more point charges, yeah, you just use principle of superposition and not a big deal, right? You can, now we know how to handle, we just solve the problem, right? But what about situations like this? What if you have, for example, a rod uniformly charged? Let's say you have 5 coulomb of charge uniformly distributed over the rod. And the question is, how can we find electric field, for example, at this point or that point? Of course, this charged object is going to create electric field everywhere, right? Reasonably complicated electric field. And quite often we want to know the value of the electric field at a certain point. So how can that be done? Because this is not a point charge, so we cannot use the formula E equals KQ divided by R to the power of 2. No, that is only for a point charge. Or what if you have a uniformly charged ring? Again, it will create an electric field, and again, it's not a point charge. So we cannot use just that formula. So how can we find electric field at a certain point? This object can look as a point charge if you go to infinity, and from infinity, yes, you can treat this object as a point charge, but that is a special situation, which is not a special case, right? Or if you have some surface uniformly charged, so how can you find electric field of object like this where we have a continuous charge distribution? So that's the goal, major goal of today's class, right? Okay, but before we start actually discussing actual situation, discussing actual problems, we need to discuss properly charge densities. Lots of problems students have with these charge densities. Especially we will need them when we will introduce Gauss's law after a couple of classes, right? So it's very important, although at the same time it's a very basic, but still plenty of students have troubles every semester with charge density. And what surprises me also, because the difference between mass density and charge density only in one word. You need to use, instead of word mass, charge. That's it. Idea is exactly the same. Okay, so now let's discuss these charge densities. Okay, I need to bring slides forward. Okay. So these are the sections which I'm planning to discuss, and yeah, this is the goal, right? Okay, charge densities. Let's start with a simple. We're going to discuss three possible situations: one-dimensional charge distribution, two-dimensional, and three-dimensional. That's what we have most of the time in our life, right? So let's start with one-dimensional. Basically, it means that one-dimensional charge distribution, it means that you have a charged rod, right? So let's assume that we have a rod over here, right, of length L and total charge Q. I know, 5 coulomb, 7 coulomb, right? Uniformly distributed. Every time we're going to discuss the simplest possible situation, but because of course there are you can come up with more complicated situation where charge distribution of charge is reasonably complicated, right? But we're going to talk only about a uniform charge distribution. So this is our system. Okay, let's add some cute creature, right? And now first, how can we introduce charge density? In this case, since it's a one-dimensional charge distribution, we're going to talk about what is called a linear charge density. Right? Linear, self-explanatory, right? Because it's one-dimensional case. So linear charge density, we're going to use symbol lambda, Greek letter lambda. By definition is what? You take the total charge and divide it by the total length over which this charge is distributed. So it's a linear charge density. Total charge divided by the total length. It's like a mass density. If let's say I have this rod and let's say it has a mass of 5 kilograms and it has a length of 2 meters, for example. So how can we find mass density, linear mass density? Of course, of course, everyone can answer that immediately. Take the total mass, divide that by the total length, and it will be 5 over 2. It will be 2.5 kilograms per meters. This is exactly the same story, but instead of mass, you have charge. That's it. So total charge divided by one-dimensional volume, basically length. It's a one-dimensional volume, right? So total charge divided by the length. Okay, it's a first step. That's what we mean by linear charge density. Basically, I can say by definition. Now, next step. What if we have this small section delta L? And I want to know the amount of charge only in this particular section delta L. Well, let's say this belongs to me. I want to know how much of charge I'm going to have in that small section delta L. Now, in order to find that amount of charge in that delta L, you need to take this linear charge density and multiply it by the length of this section delta L. And that will give us amount of charge in that small section. The same like with the mass, right? So if you're interested in the amount of mass in this section, for example, what do you have to do? You need to take the linear charge density and multiply by the length of that section. So in this case, it will be here. Lambda, it's our linear charge density multiplied by the length of that section. If you're not confident, for example, how can you check that you have to do this? Check units. Check units. What do you have to get on this left-hand side? Coulombs. It's a charge, coulombs. Units of lambda. What are the units of lambda? Look, coulombs divided by meters. So in order to get coulombs on the left-hand side, you need to multiply lambda by length by meters in order to get rid of meters in lambda, right? So here you have coulombs divided by meters times meters, you will get coulombs. Check unit. Units, unit analysis, very powerful tool to check formulas. All right. Okay, so that's how you can handle one-dimensional charge distribution. Again, it's only correct for uniform charge distribution. And that's what we're going to have. So first situation, one-dimensional. That's how you can do it. Now let's assume, let's increase number of dimensions. Now let's say we have two-dimensional situation. We have some surface of area A uniformly charged. So we have again uniform charge distribution, but now it's a two-dimensional situation. We have surface like a table charged. And again, let's assume that we know the total charge Q and the total area A. So now how can we introduce? Now it's called surface charge density. Here we had linear charge density, now surface charge density. The same way, total charge, take the total charge and divide it by the total area. And now we're going to use, this book uses letter eta, Greek letter eta. Total charge divided by two-dimensional volume, basically. Area, it's a two-dimensional volume. Look, it's exactly the same structure. Here, in order to get linear charge density, we took total charge and divided it by one-dimensional volume, length. Length, it's a one-dimensional volume. Here, the same structure, you see, total charge, but now divided it, and then we divided it by the two-dimensional volume, area, right? The same like mass density. Take the total mass of the some surface and divided it by the total area, right? So nothing complicated. It's and then of course the same next step. What if we have this small patch, small area with small patch with area delta A? And the same question, what if I want to know the amount of charge only in this particular patch? The same like here. Now you need to take the surface charge density and multiply by the area of that patch. Here we multiplied it by the length of this section, of that section, now by the area of that patch. You see, the same structure. So that is two-dimensional case. And of course, now we can, in a similar way, we can introduce a three-dimensional situation. What if we have some volume, sphere, uniformly charged? So how can we find first volume charge density? So here first we had linear charge density, then surface charge density, now of course volume charge density. The same, like here, you take the total charge Q, which is inside of this, for example, sphere, and divide that by the total volume over which that charge is distributed. Now we use, this book uses letter rho, Greek letter rho. Again, you see the same structure, total charge divided by one-dimensional volume. Here, total charge divided by two-dimensional volume. And now, again, total charge divided by three-dimensional volume, which is volume. And of course, now the second step exactly the same. So what if you are interested in the amount of charge in small volume, a small part of this sphere? The same. Take the density. Now it's a volume density, volume charge density, and multiply that by the volume charge of which you want to find. One-dimensional case, two-dimensional case, in three-dimensional case. We're going to use it, especially when we get to Gauss's law. We will have to use these formulas a lot, right? And still, nevertheless, students have lots of mistakes with finding these with these densities and the amount of charge in some parts of objects, charged objects. Okay, so now what about the time? So we still have a couple of minutes before the break. Now I need to switch back to whiteboard, and we need to look at the example. How can we actually find the electric field created by some uniformly charged object? Right. Okay, so I hope you have this because we will need it. And now let me switch. So what do we have in this problem? A charged ring. You know what? Additional word must be added. Uniformly charged ring. Okay, probably first I need to show. So let's assume this. We have this ring, which is uniformly charged. The total amount of charge is given. Then radius of the ring is also given. And then we need to find, of course, this ring is going to create an electric field everywhere. But we are interested in the electric field at a point which is at the distance z directly above the center of this ring. So just at a distance z from the center of the ring, we want to find the electric field. Right. So that's the problem. And so now I can write. So we have a uniformly charged ring. Okay, so what do we know about this ring? It has radius r and charge q. Right? And we will have to find the electric field at the distance z. So also given z. Okay, let's have a break. It's 8:50, and during the break I will draw the picture of the ring, right? Okay, guys, 9 a.m. So let's continue. Again, so we have a charged ring, uniformly charged. So we have charge Q uniformly distributed over the whole ring. And so we need to find an electric field, net electric field, right? Net electric field at this point P. Of course, the question can be about finding electric field at any point, for example, at this point, at that, or this point, right? But trust me, if somebody asks you to find the electric field at this point, it's a clear indication that that person just doesn't like you, because you're going to suffer a lot. But because of the symmetry of the system relative to this point, this problem is not that bad, right? But anyway, so let's start. So obviously it's not a point mass, so we cannot use directly formula E equals kq over r squared. So let me write. So far we know only this, right? So yeah, let me write it here. So we only know this. So E equals kq over r squared, which is for a point charge. Right. So this is the only thing we know. And of course, we cannot just grab this and start using it for this ring because the ring is not a point charge. So how can we start attacking this problem, right? Solving this problem. So what's the beginning? Oops. And the beginning is very typical for problems like this. First of all, you need to pick what is called an infinitesimally small section of this ring. Okay, so let me take this. So this is my, it does look like infinitesimally small, but this is my infinitesimally small section of this ring. Of course, it has a length, okay, let me use blue. It has length dl, and of course it will have some small amount of charge dq. If you take small section of the ring, of course there will be some small amount of charge, and of course it has small length. So now, you remember from calculus classes, what does it mean infinitesimally small? Basically, it means that it is smaller than anything you can think of. If you think that this is small, no, infinitesimally small will be smaller. If you think this is small, infinitesimally small will be smaller. If you think this is, then it doesn't matter how creative your wild your imagination is in thinking in terms of in thinking about this, how about this small length. Infinitesimally small will be smaller. That's basically what infinitesimally small is by definition in calculus. So if this is our infinitesimally small, smaller than anything you can think of, so if it's so damn small, so how can we treat this infinitesimally small fraction? We can treat it as a point mass. This is the beginning of any solution of a problem like this. Take infinitesimally small part, in this case part of the ring, and treat it as a point object. In this case, we can treat it as a point charge with charge dq. That's the beginning. Let me write that down even. All right. So in order, okay, and of course, if we can treat it as a point charge, we can use this formula for this point charge. Okay, let me write that down. So take an infinitesimally small, oops, small section dl, of course, which has with some amount of charge dq, and treat it as a point charge. And treat it as a point charge. Basically, this is the beginning of any problem where you have to set up an integral. It doesn't matter if it's integration of finding electric field or some or force, right, or of some complicated object. Every time the beginning will be the same. So take infinitesimally small section or patch or volume, right, and treat it as a point mass, or point charge, point mass, point whatever, right? So if we can treat it as a point charge, we can use this formula. So we can write as, but now it will be, okay, let me write it first and then I will explain. So dE equals k dq over r squared. So what is this d? It's an electric field at this point created by this point charge dq. And r, it's a distance from our point charge, which, so we're treating it as a point charge. So I can draw something like this. So this will be our r, this r. And this is the electric field created by this dq at this point P. Small contribution to the net electric field at this point. Okay, let me first draw it, dE. So this will be this dE. Again, it's a small contribution to the net electric field from this point charge. But of course, there will be similar small sections over here. There will be small contribution from this section. There will be small section over here. Of course, there will be contribution and so on. Right? But now we take only this small section, treat it as a point charge, and we can use this formula. But of course, now instead of E, we write dE because it's a small contribution to the final result. And of course, now instead of Q, now our charge is dQ. And divided by the square of the distance from the point charge to the point in question. Typical beginning of any problem where you have to set up an integral. Okay? So now what's next? Of course, at a certain point, we will have to integrate it. But before we can start integrating, we need to write all these components, ingredients in terms of what is given and a single variable of integration. What is given? RQZ. Z is given. It's a distance, particular distance from the center of the ring to the point in question. And also we will have to introduce a single variable of integration. Which variable can be used from the very beginning, it's difficult to tell. But most likely, naturally, we'll come up with something, and we will see if it's a good variable of integration or not. From the very beginning, quite often, it's difficult to tell which variable of integration is the best. Right. But so, okay, next step, we need to write all these components in terms of what is given. Let's start with r squared, since it's the easiest one. So r squared. So it's this r, so how can we write that in terms of what is given? R capital is given, z is given. This is the right triangle, right? So this is the right angle. I can show it like this, right? So, of course, Pythagorean theorem, r squared equals r capital squared plus z squared. This is very simple. So we can write r small squared equals r capital squared plus z squared. Okay, so done with this. K is just a universal constant. We cannot do anything with that, right? We just know that constant now, dq. dq. We need to write it in terms of what is given. Okay, before I write what dq is, let's understand which formulas which we just discussed, like what before I switch to the whiteboard. You remember the last slide about a linear density, surface charge density, and volume charge density. Which situation do we have here? Is it a linear charge distribution, or surface charge distribution, or volume charge distribution? First of all, we need to understand which situation we have: one-dimensional, two-dimensional, and three-dimensional, or three-dimensional. It's a subtle point. Quite often, lots of students think that this is a two-dimensional charge distribution. No. It's a two-dimensional object. A ring, yeah, it's a two-dimensional object, but we're talking about charge distribution. And charge distributed over a line which forms a circle. So it's a one-dimensional charge distribution. I can give you this example, for example, right? What if I take this rod? Okay, it's a ruler, right? But let's assume it's a rod uniformly charged. So right now it's a straight. Of course, if I ask you which charge distribution do we have here, one-dimensional, two-dimensional, or three-dimensional, of course, everyone will be able to tell it's a linear charge distribution, one-dimensional case. But what if I slightly bend it? Is it still one-dimensional? Yeah, it's still one-dimensional charge distribution, still linear. And if I keep bending, it's still, yeah, object becomes more complicated, but it's still charge is distributed over a line. That line is not straight, it's sort of like a curved line, but it's still one-dimensional, it's still linear charge distribution. If I keep bending, okay, I like this rule, I don't want to crush it, break it. Of course, if I keep bending, at some point, of course, I will get a circle. So it's a two-dimensional object, but one-dimensional charge distribution. This charge is distributed over this curved line, which is a circle. Agree? You have to agree, because it's a one-dimensional charge distribution. Right? I think it's more or less obvious after pointing at that moment, right? Okay, so it means that we need to use from that slide, which we just discussed, right, 15 minutes ago, for the first box, right? One-dimensional case. And we need to use linear charge density. So, and the second formula in the first box, right? You remember I asked you, so how can we find the amount of charge in a small section of that rod? We need to take linear charge density. We used lambda, right? Lambda, n times the length of that section. In our case here, also dl small. So lambda times dl. Okay, I will open my explanation box and I will write lambda is a linear charge density. And I will close my explanation box. But the thing is, okay, agree, right? So it's just from that slide. But the thing is now lambda is not given, right? What is given? RQZ. So we need to write lambda in terms of what is given. And you see, naturally, we introduced the first form of variable of integration. So we use L, okay, dl, infinitesimally small, right? So naturally, the first option appeared, and we will see if it's good enough. Maybe it is. So, but first, we need to find linear charge density. So how can we find that? That is the first formula in that box, in the first box. If you have a rod of length L, uniformly charged, you take the total charge and divide that by the total length. But now our rod is not straight, but curved. But the idea is the same. Take the total charge and divide that by the total length. In our case, total length, it's a circumference of the rod. 2 pi r, r capital. Right? Okay, so now I can write lambda equals q divided by 2 pi r capital. Yeah, it's the first formula from that first box. Total charge divided by the total length. But now it's not a straight line, it's a curved line, circle, circumference. Right. Okay, so now let me rewrite this. So it will be u over 2 pi r times dl. Okay, so now we wrote in terms of what is given and a variable of integration. For now, variable of integration as L, right? So now we can plug this over here and this over there. Okay, let me show it. So now this goes over here and this goes over there. So let me rewrite now dE. dE. Again, it's a magnitude of this vector, what we are writing, right? So it will be k. This dq, it will be q over 2 pi r times dl and divided by r squared plus z squared, r squared plus z squared. So that's what we have for now. Of course, 2 pi r can be dropped in the denominator, but we will do it next time. So now, at this point, it looks like, can we start integrating now? So can we write just E equals integral over dE and start integrating over a circle? Actually, strictly speaking, it's a calculus 3, right? And some of you didn't take calculus 3, some of you did. But the thing is, we will see that we're going to take these integrals from calculus 3 without actually taking it. But up to all these steps you should be able to understand. It's not calculus 3, it's just a calculus. Okay, so now, can we start integrating now? No. Because what's the nature, what's the sort of nature of this quantity? It's a vector quantity. It's a vector quantity. It's not a scalar quantity dE. So this is just the length of this vector, magnitude of that vector, right? So if dE were a scalar quantity, yeah, we could have just started integrating. But since it's a vector quantity, it would be wrong. First, how can you integrate vector quantity? You need to find components, x component, y component of this. And only then you can start integrating components. You cannot integrate vector like this, find the magnitude and start integrating. No, it doesn't work like that. It would be wrong according to mathematics, and we will be criminals in the world of mathematics, right? No. According to the rules of calculus, you need to take first, find components of the vector, and only the components, components of this vector, and only then you can start integrating. All right. Okay, so now let me write something like this. So from this point, we're supposed to do this. In order to find y component, we need to integrate, dEy. So dEy, it's a y component of this vector, and then only you can start integrating. And then, of course, you will have to, you will be able to find x component when you find dEx, and only then you can start integrating. So we need to find dEy and dEx. But you know what? I'm lazy, like most of us, right, to integrate this. So, lazy. So, let's skip this. The first part. I'm talking about this, right? And I will try to skip it using the symmetry of the problem. But of course, if you don't like the idea of using symmetry, yeah, you can find y component and then integrate, and you will get exactly the same result. But quite often, mathematicians, physicists, engineers, they use the symmetry in order to simplify or reduce the amount of work, right? So, but with this, the trick will not work. But with the y component, yes. Okay, so what do I mean by using the symmetry? So let me Okay, probably I'll try to fit. So, use the symmetry. Okay, what do I mean using the symmetry? Look, we took this infinitesimally small section of this ring, right, on this side. But also, if I draw a diameter, right, all the way to this side. So, on this side, there will be symmetrically positioned exactly the same section dl with the amount of charge dq, right? Diametrically opposite section, right? For any section on this side of the ring, we can find diametrically opposite section with exactly the same dl and the same amount of charge, okay? So, of course, this dq is going to create a very similar contribution to the net electric field. I will use blue color for that. And of course, that contribution can be represented by this vector dE. right? Okay, and now at this point I realize that one very important part of the picture is not on the board. Sooner or later, of course, I realized that which part? I already mentioned that several times. Whenever you work with vectors, you have to introduce what? Coordinate system. Right? Because you see, I already started saying x component, y component. Where are the coordinate system, right? Right. Okay, so let me introduce coordinate system. Oh my God. It is as ugly as Toyota cars. Right, so this will be y component. This is x x coordinate. Right, so now it's good. So contribution from this section, contribution from that section. Now let's find components, y component and y components and x components of these two vectors. Okay, so let me first do with blue. So this will be x component of that vector. This will be y component of that vector. And now let's do the same for the red. So this will be the x component, and this will be y component, right? And integration is basically adding small contributions, adding, right? So if we add this red x component with blue x component, of course, they will add each other and no troubles. But what happens if you add this y component and that y component? They cancel each other out, right? Because this dq is the same as that dq. This r is the same as that r because they are diametrically opposite, right? So this length of this vector and that vector is the same. So y component and y component in magnitude the same, but this is up and this is down. So these y components, they brutally cancel each other all the time. So it means what? When you integrate every time for the section over here, you'll find section over there, and y components will be canceling each other all the time. So it means that after integration, you will definitely get 0 for the y component. So there is no even point of sweating and integrating this. By just looking at the symmetry and running this analysis, you can tell from the very beginning that y component of the net electric field at this point will be 0. It's a very, very common trick which is used during the integration to reduce the amount of work. But of course, if you don't want, if you say, okay, it's a complete BS, I don't like it, I hate it, right? Okay, not a big deal. Find y components of this electric field, right? And integrate it properly. And you will end up most likely integration of an odd function over symmetrical limits, and you will get 0. You will get 0 mathematically. It's also great, right? But we're not going to do it, right? So I will just write using the symmetry. We can show by using the symmetry. We can justify that y component of the net electric field at the end will be definitely 0. Right? So using the symmetry, we can write that E sub y will be 0. So it's a pretty much part of an answer. So I can frame it with red because, yeah, we're trying to find the electric field vector at the end, and we already know that the y component of that vector will be 0. So it means that what's left only x component. So now we need to deal with this integral. And this integral is not going to give us 0 because you see what happens with the x components. They add each other. So during the integration where you're going to keep adding these x components, they don't cancel each other. Right. Okay, so now let's deal with x components. So let me write only x component is left. Right. So now, let's find dEx. So pretty much we need to find this integrand dEx, and then I will write down integral and we actually integrate it. Right, one step at a time. So this is dE. Okay, let me also show where is this dx. So this is dE, and this red, let me make it thicker. This is our dEx. So now we can forget about this blue electric field, dE, this blue, because we need it only to justify the zero, this zero. So now we're back to this red, right? And so now we just need to find this x component in order to start integrating. So in order to find this x component, again, we need an angle. Like in the previous problems, you remember every time we choose some angle in order to find components. Now I suggest let's introduce this angle theta. It's not given. So it means we need to write it in terms of what is given. And it's simple. Okay, let me first write dEx using this angle, and then we will take care of this angle. For now, it's sort of mysterious angle. So, of course, it will be dE times cosine of this angle, because we are trying to find the side which is adjacent to the chosen angle. So, times cosine theta. Okay, now I will open my explanation box in order to write down what is that cosine of that angle. So obviously by geometry this angle and that angle are the same. They are vertical. Okay, not the same, they're equal. Equal, because they're vertical, right? And again, so once you realize that this is the angle which we need to find, actually cosine of which we need to find, it's a piece of cake. Because look, this point, this point, this point, it's a right triangle. We are experts in dealing with the right triangle. Cosine of this angle, it will be ratio of adjacent side versus hypotenuse, right? Trivial properties of a right triangle. So cosine of theta equals adjacent side z divided by the hypotenuse. And hypotenuse is already written in terms of what is given. Square root of r squared plus z squared. Right? So now I can rewrite it as z divided by square root of r squared plus z squared. Again, every time, everything inside of the integral must be written in terms of what is given and a single variable of integration. So far, our variable of integration is dl. We introduced new angle and immediately we wrote it down in terms of what is given. Z, R, Z, they're all given. So far so good. So let me close my explanation box. And now let me write dE, explicit form, and cosine over here. Okay, now we have to be careful not to lose anything. Okay, this 2 pi r will go downstairs in the denominator, right? So let me write that down. So it will be k q dl divided by that r squared plus z squared. So this is dE, I wrote it. Yeah? 2 pi r. That was, I was afraid of losing some. 2 pi r and r squared plus z squared to the power, no, r squared plus z squared. Right? Yeah. Then cosine. Cosine is this. So it's a z divided by square root of r squared plus z squared. Of course, this and that can be combined and you will get power of 3 over 2, right? Okay, maybe I will rewrite it over here. So it will be k qz divided by 2 pi r and r squared plus z squared to the power over 3 over 2 and dl. Messy? Yeah. Not that bad, actually. Okay, so now we have integrand dEx. Now we need to write an integral. So e sub x equals to the integral of dEx. x. Again, now it's legitimate to do integration because now this is the component of the vector, not the magnitude like what we have here. Integration of the magnitude is illegal. Right. So it's an integral. And so far we have an integration over L. Right, so now I'll just need to rewrite that all that mass K, Q, Z, dl, and divided by that all that 2 pi r squared plus z squared over to the power of 3 over 2. Okay, that 3 is not nice. Let me rewrite it. 3 over 2. Okay. Again, the question about your feelings. How do you feel about this integral? Does it look terrifying? Usually that's what students feel when they see the integral like this. They kind of, oh my God, what is that? So the life is over. Let me switch to the philosophy department or something like that. No, guys. It's actually trivial integral. Let's just come down and look at this integral carefully, term by term, factor by factor, not term by term. K. What is K? It's a constant, universal constant. What can you do with the constant inside of the integral, constant factor inside of the integral? You can extract it. You can take this K and put it in front of the integration, simplifying the integral. Q. It's a given constant, I don't know, 5 coulomb, 7 coulomb, constant. Again, that constant factor can be extracted. Z. It's a given number. Your boss told you, okay, go and measure electric field, I don't know, 5 meters from the ring. That is a given number, constant. Again, can be taken outside. 2, constant. Pi, constant, outside. R, it's a given constant. Again, can be taken outside of the integral. R squared plus Z squared to the power of 3. It's 3 over 2. Constant, constant. Again, it can be taken outside. So you see, all this mass is a constant. And all this constant factor can be taken outside of the integral, making our integral banal, trivial, piece of cake, Mickey Mouse integral, or whatever, right? Insulting words we can come up to insult this integral. So we can rewrite it K, Q, Z. I'm just taking all these constants outside of the integral. 2 pi r and r squared plus z squared to the power of 3 over 2 and integral over the whole ring dl. Okay, let me write over the whole ring. Okay, now I circle this integral and I'm asking for an answer. It's a root, right? Because strictly speaking, this is still integration from calculus 3, which is, again, strictly speaking, not trivial. You need to learn some tricks. You need to know how to integrate. And at some point in calculus 3, you will learn how to do this integration over a line, over a surface, over a volume. But in this course, we're going to use these integrals. We're going to see integrals like this several times. But we're going to use our knowledge from high school. Everyone knows the answer of this integral. Everyone who is in this class knows the answer. What's the meaning of this integral? You integrate over dl. It means what? You take small, okay, integration is just a fancy word for adding small stuff, small contributions. In this case, you're adding small dls. What is dl? Infinitesimally small sections of this ring. So it means what? You just keep adding this small length of these small sections. It means what? It means that you take dl, I know, 5 micrometers or nanometers, plus next small dl, length plus next small length plus next plus, and you keep adding these small dls until you'll get back to the starting point. When you add all these small dls length, what are you going to get at the end? Circumference of the ring, 2 pi r. Again, yeah, from the mathematical point of view, still here inside of this plenty of integration. But since you don't know that, we can use high school knowledge. And if you know the meaning of integration, again, it's adding small things, you should be able to write the answer. It's a 2 pi r. So this integral equals to 2 pi r. So now we have 2 pi r here downstairs, and that 2 pi r, of course, this integral is in the denominator. So of course, this 2 pi r and that 2 pi r can be cancelled, and we're getting the final result. The problem is over. Again, you see, again, sometimes students confuse, how come that I cancel this and this? Again, this integral is in the denominator. I could have written over here that integral, right? So this 2 pi r is basically over here in the numerator, and this 2 pi r is in the denominator. So we can cancel that. Okay, so the final result, all right, equals to k q z divided by r squared plus z squared to the power of 3 over 2. So that's our x component of the net electric field at the point P. Let me frame it. So that is the x component, that is the y component. So that is the answer for this problem. It's not the worst integration, believe me. Right. Usually I try to expose students to integrations in this course twice. This is the first time. It's probably the most complicated problem from the point of view of calculus. But again, you're science majors, you're from an engineering department, so you must be exposed to stuff like this, and you shouldn't be scared by the problems. This is not trivial, but at the same time, not the worst possible scenario, right? Because we have uniform charge distribution, and it's not that bad actually. Right? And usually on the exams, I don't give problems like this. In the past, I gave a few times on the quiz, but my goal is just to expose you so that you would be familiar with the integration. Right? In physics too. I think exactly the same, or similar problem will be in your homework. You'll have to just repeat, but again, procedure is the same. So again, at the every time for the problem like this, where you have to set up an integral, you have to start with this, take infinitesimally small part and treat it as a point. In this case, since we need to find the electric field, so we can use the formula for the electric field created by a point charge. So once you wrote this, then the next step, you need to write everything what we have inside here in terms of what is given and a single variable of integration. Here, we naturally introduced a single variable of integration, and that variable of integration happens to be enough for us, good enough. So we use dl. So we didn't change it to something else, but sometimes we have to change it to a different variable of integration, right? And then once you get to this point, once you wrote everything in terms of what is given, if it is a vector quantity, you need to find x component, y component, and only then you can start integration. If it's a scalar quantity, this is enough. You can start integrating over here. But vector quantity, we have to be careful, and it's more complicated. And then the rest is just integration. Right. At this point, most of you already went through calculus where you learn integration. So, and it should be like this. in physics 2, lots of integration, and by this point, students must be comfortable with integration. Okay, let's switch to the presentation, and we'll continue with my slides. Okay, so this is the example which we just discussed. Right. And actually, okay, let's just relax a little bit. Easy clicker question. I forgot about this. Much easier after this. So what do we have here? And again, the poll is in the chat. Just slightly scroll it up. Right. Today you were not very active in the chat, so it's right there. You see, we have these lines. These are electric field lines, which we use to visualize the electric field. Then, and you see direction of these electric field lines. Then you take two protons. Of course, two protons, it means they are identical. They have the same mass, the same charge. One proton is positioned at this point A. The second is positioned at point B. And so, simple question, which proton is going to have larger acceleration? Give it a try. Sorry. Give it a try, and then I will discuss. Okay, I need to bring chat forward. Okay, I see. Okay, yeah, I expected that you will get the right answer, but I want to justify in a structured way. Oh, somebody changed. Oh no. That option is back. Okay, number of answers is not growing, so it means that everyone answered. Okay, now let me discuss. Okay, I usually, not usually, sometimes, often, I try to create sort of like a skeleton of the solution or diagram of the solution, right? And usually I start from the end. We need to answer the question about acceleration, right? Acceleration. Oh, again, I need to bring slides forward. All right, so we need to answer the question about acceleration. So in order to get information about acceleration, what do we need to know? We need to know information about the force acting on an object, right? So that we can use Newton's second law, F equals ma. If force F acts on the object m, then it leads to acceleration a. So in order to get information about acceleration, we need to know information about the force. And then we can use Newton's second law to make this transition. Then, so now we see that we need to get information about the force. What do we need to know in order to get information about, of course, in this case, it's an electric force, right? So how can we get information about the electric force? Of course, we can get it if we know information about the electric field, right? And of course, we can use that formula for the electric force in order to make a transition from this point to the point F, right? So F equals Q times E. Yesterday we introduced this formula. So pretty much this is the skeleton of the solution, right? So first we need to get information about the E in order to get information about the acceleration. So what do we know about the electric field? Of course, electric field is stronger where the electric field lines is denser. So of course, at point A, electric field, density of electric field lines is larger. So it means that electric field here is stronger than the value of the electric field at point B. So E at point A is larger than E at point B. So now, using this formula, of course, we need to go to this stop about the electric force using this formula. Since charges are the same, and positive, right, charges are the same, right, because they're both protons, of course, electric force at point A will be also larger than the electric force at point B. So now we have, we know about the forces, and now the last step, using Newton's second law, we can get to the point of acceleration. Again, since we have two protons, masses are the same. So it means that if force at point A is larger than at point B, it means that acceleration at point A will be also larger than the acceleration of the proton at point B. So again, I expected that most of you will answer it correctly, but I wanted to drag you through these speculations about how would I justify it in more or less structured way. Right. Okay, so yeah, the answer is A. The proton A, of course, is going to accelerate. It's going to have larger acceleration. Right. Okay, great. And now let's move on with the results which we just derived. What if now instead of A, where's my ring? Here is my ring. What if instead of a ring, we have a disk, uniformly charged disk, and we have the same question: find the electric field. So you see the disk, uniformly charged disk, and basically the same question: can you find the value of the electric field at the distance z from the center, but now from the center of the disk? Again, you see the difference? We solved the problem about finding electric field created by the ring, but now it's a question about finding electric field created by the disk. So now, of course, you will have to do integration and use the result which we just derived, the electric field created by the ring. So that's why you see in the middle there is a red ring, because you need to use these results and add additional integration. We're not going to do this integration. It is done in the book. If you want to see that integration, you can read it by yourself. The example which we discussed is enough. So basically, using this result, you can apply and do additional integration, and you will end up with this expression for the electric field created by this uniformly charged disk with surface charge density eta. Right, again, you remember that slide 20 minutes ago when we discussed the charge densities? This is eta, surface charge density, amount of charge per unit area. Right. Okay, as I told you, okay, probably you were, okay, Pablo asked about the attendance code. Probably you were not in the class yesterday. I'm not planning to use attendance code. I am going to download attendance report from Microsoft Teams. I can see who was in the class, when you guys entered the class, when you left, right, and so on. I don't like that university uses VPN now. In order to get to that attendance app, you need to use VPN. No. During the class, it's too complicated. During the class, everything must be as simple as possible. So I decided to use just a Microsoft Teams report. Right. Okay. Let me just hold you for additional a minute, because right now, stopping at this point, it's sort of like a hanging in the middle of nowhere. All right, so that's what you can get, again, without a derivation. That's what I wrote, without derivation. So now, let's look at the limit. Let's look at this expression at the limit. Again, in some calculus course, you already learned how to deal with limits. So let's look at this limit. Z, which is the distance to the point in question from the center of the ring, is much smaller than the radius of the disk. So basically, what does this limit give us instead of a disk? If R is much larger than Z, it's basically infinitely large charged surface, charged plane. This limit leads us from the disk to an infinitely large surface. Okay, so let's see what are we going to get in terms of the expression for the electric field with this limit. Okay, if you apply this limit, of course, you need to play with the second term in this expression. Z is much smaller than R, so downstairs in the denominator, this Z squared can be neglected. As a result, we have a square root of R squared. Square root of r squared is r. So we'll have z over r capital. Z over r capital, z is much smaller than r capital. It means that this second term is going to give us 0 in this limit. As a result, we have only first term 1 left. So we need to multiply eta over 2 epsilon naught times 1. So as a result, we have this expression. This is the expression for the electric field created by an infinitely large charged surface with the surface charge density eta. So what's the major feature about this expression, about this formula for the electric? We're going to use this formula quite often during the semester. Does it depend on the distance from the surface? Does it depend on z? No, it's not there. Eta is a given constant. It's a surface charge density. Epsilon naught, it's a universal constant. All this is constant. So E electric field is constant. So we're getting to the conclusion. So the electric field created by an infinitely large charged surface gives us a uniform electric field. It's a first example of a system which can give us a uniform electric field, because you remember we already mentioned about uniform electric field, and this is the first electrical system which can give us a uniform electric field. So here's the picture. For example, we have a infinitely large positively charged surface, right? Plane, and you see electric field lines above, they pointing up, below down. You see electric field lines, again, they start on positive charges, and you see density of these lines exactly the same. It means that it gives us that electric field is uniform, right? And the strength of this electric field can be found by using this formula: surface charge density divided by 2 times epsilon naught. So again, the most interesting thing, that this field strength is dependent of the distance. It's a uniform electric field. Okay, so this is the first example of a system which gives us uniform electric field. Tomorrow we will introduce a second system, a parallel plate capacitor. It's just a easy transition from this point to the next point, right? And from that point, most of the time our electrical systems are going to be either point charge or a capacitor, parallel plate capacitor, right? Okay, so I just wanted to finish the slide because it's logically must be finished, right? Okay, guys, thank you.